solutions, suspensions, and colloidal. Again, for the most part, they like to just say that there's only two things. There are heterogeneous and homogeneous. But we can technically define things that are in between the two, suspensions and colloids, colloidal. So a solution is a homogeneous mixture where one thing fully dissolves in another. So it's called a solution, and it's homogeneous because the molecules or the solute become evenly distributed throughout the solvent. That's the key thing for a solution, is that the molecules are evenly distributed throughout the whole thing. That's the difference between a colloid, where there are regions of high concentration, where the particles get larger or the droplets get larger inside of it. The particles are also not visible, even under the highest magnification. So even the world's best microscope would not be able to see the individual particles. However, if you look at milk and shake it, you might be able to see particles in it. So a solution is transparent. You can shine light through it. So they're considered homogeneous and stable. Their dimensions is between, so the particles inside of a solution are on the order of atoms and molecules, so between 0.1 and 2 nanometers. They're almost always transparent, meaning light can usually pass through the entire solution. If the solution is, or if the solute is able to absorb visible light, then the solution will have a color. So, for example, if you have some Kool-Aid, some red Kool-Aid, some of the flavoring crystals can absorb all the can absorb different colors, which gives it, which means the solution is going to appear not clear; it'll have a color of its own. A suspension is a mixture between two substances where one is finely divided and dispersed in the other. This could be like sand and water, dust and air, droplets of oil and air. However, the particles in the suspension will eventually settle out if allowed to stand undisturbed. So you were to mix up some mud and water, or some sand and water. The sand doesn't actually dissolve, but it'll stay mixed. If you sit there and wait for a little bit, eventually the sand will drop to the bottom, leaving it'll eventually just come out. Also, droplets of oil in the air. The oil will eventually settle and fall down to the surface. Dust in the air is the same thing. Particles are too large. You might see the dust particles distributed throughout the air, but if you were to sit there and not disturb anything, that dust will eventually settle down onto the floor. If I go too fast, I'm coming back up. So, particle size for true solutions are going to be very small, less than a nanometer. For suspensions, it's going to be much larger. But then we have colloids that sit in between. Colloids are the right size to where they won't settle out like solutions. But unlike suspensions, the particles are large enough to settle down to the ground. Colloids are not true solutions. They're not evenly distributed. The particles are kind of large, like clumps of particles together. So suspensions, many particles of suspension can be separated through a filter. So if you were to take a coffee filter and pour mud through it, or muddy water, you can filter out the sand and have clean water go through. For a true solution, you can't do that. If you tried to pour Kool-Aid through a filter, Kool-Aid would come straight out. You can't separate the flavor and everything through it. Like coffee coffee is a true solution. You can't run it through. I should say it's the reason why you can run it through a coffee filter and still have coffee come out. You wouldn't just have just pure water going through. However, you also have coffee beans that would be make it a suspension, and the filter would trap out the grains of coffee. They also do not allow light to go through them easily. That's why muddy water, you can't really see through it. A colloid is an intermediate between a solution and a suspension. While suspension will separate out, a colloid will not. We will not be going into the different types of colloids. This is the effect I wanted to show. Have y'all ever shined a flashlight through milk? Try it when you get home. Take a clear glass of milk and shine a flashlight through it. Oh no, it won't work with milk. It'll work through flour and water. Let's see. It's this. It does work with a colloid too. It's called the Tyndall Effect. If a strong beam of light is passed through a colloidal solution and viewed from the side, a bluish light cone illuminates the path of the beam. This phenomenon is called Tyndall Effect and results due to the scattering or diffraction of light by colloidal particles. So, blue light, because of the wavelength of blue light, blue scatters more easily. For the size of particles of colloidal, so in a colloidal system, the size of the particles are in a very narrow range. It just so happens that a range is good for scattering blue light. So if it's a colloid, the light is going to be scattered, and it'll give off some blueness. This is known as the Tyndall Effect. So let's see if I can actually. That's really all wanted from that. So if you were to shine a light source through a solution, you wouldn't be able to see the light beam in it. However, if you did it through a colloid or suspension, you'd be able to see the light beam. Same way here. So this is a good indication of whether or not something is a colloid or a true solution. Is if you can see the light beam through it, actually in it. So a laser beam, you can see a little bit of the laser beam, but here you can clearly see the laser beam in the colloid. This is a good image. It's very hard to notice to get good images of blue. Blue light likes to scatter the most, so you can't see the light in this solution. In this colloid, you can see blue scattering the most. It's really hard to tell. This is white, and this has a more bluish tint in the whiteness. And it's really hard to see the blueness here, so much white light is off. Here you definitely can't see it when it's reflecting off the glass. Flour is a suspension. You leave flour and water undisturbed, the flour will separate from the water. But this is just known as the Tyndall Effect. Is why if you shine light through milk, you, depending on what flashlight you use, you might notice that there's a slight blueness to the milk. Can you ever notice that? Where the milk kind of appears slightly blue? I've seen it before when the light hits it just right. And there's one other thing. I'll just say it. I said it the other day in one of the classes. So I said like oxygen. Oxygen likes to come in pairs. So you have two atoms of oxygen for every molecule. So O2, hydrogen. The proper term for this is diatomic. Diatomic elements. There's 7 of them, but diatomic elements, so that'll be hydrogen, nitrogen, oxygen, fluorine, iodine, bromine. For right now, just because it's on this little homework, you just need to know that. Does everyone know Greek? You can't read Arabic, you don't know Greek, you don't know Latin, probably, I'm assuming. So, diatomic. Di in Greek is the prefix meaning 2. So 2 atomic is, yes, so this is literally states 2 atomic elements, or 2 atom elements. It just means it has 2 atoms. So diatomic means an element containing 2 atoms. So hydrogen comes as H2, oxygen comes as O2. That's why we say oxygen is O2. It refers to the fact that there are 2 atoms of oxygen in the element oxygen. And nothing else with that. One thing. So it should be clear. So for example, oxygen, or O2. What do you call this number right here? When you take a number and put it to make it smaller and drop it down beside a number, what do you call that? Versus this. This is a subscript. And it indicates there are 2 oxygen atoms. This would technically be a superscript. So again, if you know, I think it's Greek. Sub means below. Script means writing. So you're writing something below something else. Super means above. But subscripts indicate how many atoms there are. So H2O, this is a subscript, meaning that there are 2 hydrogen atoms. I believe that's everything needed.